Now let's just move on further towards the concept which is called as the equal chords and their distance from the center. So let us suppose if I am just taking any particular line and there exists any particular point P such that I am drawing the different line segments from or the lines from the point P towards the line AB in such a manner. So as you can see over here, if I'm just talking about this particular P point and if I'm just taking this particular line segment, so if I'm just drawing or joining this P point with this line segment, so I can join this as these many terms, means I can join P with the AB as this point, that is nothing but L1. So this is nothing but the first distance of the point P from the line segment AB. This is again the next distance that I can draw. This is nothing but again the next distance I can draw. This is again the next distance, and furthermore, since if I'm just talking about the distance of the point P from the line segment AB, then what is that distance? So the least among all these line segments is actually nothing but called as the distance of the point P from the line AB. So as you can see over here, the least distance over here is nothing but this perpendicular, which is nothing but PM. So that's why this PM is actually called as distance of AB from the point P. So the least distance over here is called as the distance of the line segment from the point P. Now from this we can say that the length of the perpendicular from the point to a line is the distance of the line from the point. It is actually the distance of the line from a particular point, which is nothing but a point P. Now similarly, if I am just moving on further towards the equal chords, if I'm just talking about the chords or the equal chords of a circle. So first of all, we know that if we are just talking about a circle, then we can draw infinitely many chords in a circle. So which leads us towards a theorem which actually says that equal chords of a circle, which or of the congruent circles, they are equidistant from the center or the centers. So actually we just need to prove that the equal chords of the circle, they are equidistant from the center. So let us suppose if we are just moving on further and talking about the proof of this particular theorem. So let us suppose if I'm just taking a circle, if I'm just drawing a circle over here, and we are talking about the equal chords. We are talking about the equal chords. So let us suppose if I'm just taking the center of the circle as nothing but O, and I'm just drawing the two chords over here as nothing but this, which is nothing but AB, and again I'm drawing the chords over here as nothing but CD. Let us suppose this is AB and this is a CD that I am taking up over here. And furthermore, if I'm just drawing a perpendicular over here, and again from the center I'm just drawing a perpendicular bisector over here again, and let us suppose if I'm just joining this OA again, and let us suppose if I'm just joining this CD again, and let us OD again. Let us suppose if I'm calling it as nothing but N, I'm calling this point as N and I'm calling this point as M. So what do we want to prove over here? We just wanted to prove that these chords are actually equidistant from the center. So actually we just wanted to prove that this particular ON is nothing but is equal to this particular ON is equal to this OM. So let us suppose if I'm just starting with the given condition, we have a circle with the center O, with the center O, where ON and OM are the bisectors of AB and CD, being the equal chords. So what do we have to prove over here? So rather than taking a construction, I'm just taking them under a given condition. So what do we just have to prove over here? That ON is actually nothing but is equal to OM, that they are equidistant to each other. So let's just start the proof of this particular theorem. So first of all, since we know that AB is actually nothing but is equal to CD, which is nothing but a given condition, and furthermore, since we know that AN is actually is equal to NB, because ON is the perpendicular bisector. It is the perpendicular bisector that we have taken. So it implies that AN is nothing but, AN is definitely nothing but half of AB. AN is definitely nothing but half of AB. And furthermore, let us suppose, if I'm just saying, since again we know that CM is equal to DM. Why so? Because OM is the perpendicular bisector that we have taken, so furthermore, we can say that DM is nothing but half of that of CD. It is half of that of DC. Let us suppose I'm taking DC and I'm calling it as nothing but the equation number 2. So from equation number star, let us suppose if I'm just taking the equation number star, AB is equal to CD implies half of AB should also is equal to half of CD, which implies that AN should be is equal to DM. From the equation number 1 and 2, we can say this fact that AN is actually nothing but is equal to DM. So if AN is equal to DM, then we can move on further towards the triangle. So we can say that in the triangle AON and the triangle DOM, first of all we know that AN is equal to DM, already proved concept. And further we know that we have the other thing, which is each 90-degree angle, means the angle ONA is equal to the angle OMD, each 90 degree. Furthermore, OA should be is equal to OD. OA should be is equal to OD, being the radii of the circle. So what can we say about the two triangles? We can say that the triangle AON is congruent to the triangle DOM by RHS congruency criteria. So if they are congruent to each other, it implies that ON is nothing but is equal to OM by CPCT. By CPCT, we can say that ON is nothing but is equal to OM, which is nothing that we have to prove over here, that the two codes are actually equidistant from each other. So in order to prove that they are equidistant from each other, so we have done a little bit of construction. So let us suppose if I'll write it over here, that what construction that I have taken, and according to that construction I have taken the given condition. So I have taken the construction as draw the perpendicular bisectors of A, B and CD as ON and OM. So that's why I have taken this as in the given condition. So I'm just writing it up in the given condition. You can also form it as a different construction part. You can take the given condition as just only the circle with the center O, and then the other part you can take it under the construction, which is nothing but draw the perpendicular bisector of AB and CD as ON and OM. Then further you can proceed further. So this is all about this theorem, which says that the equal chords of a circle, they are equidistant from the center.